That's okay. Here? What oxygen? Okay. That's a good question because this is what messes a lot of people up is understanding the chemistry. So this is the equilibrium. This is what's going on in my beaker of buffer, right? Now, I dump in hydrochloric acid. What effect does a chloride ion have on this whole pH business? None. So it's just hanging out in there. But I'm dumping in loose hydrogen ions. So this loose hydrogen ion looks around for something to react with. It says, oh, here's some base. So it reacts with the base in a one-way street, making BH+. This is not the equilibrium. So what happened to the oxygen? What oxygen? There is no oxygen in this activity. This proton is hooking up with this base to make the protonated base or the conjugate acid of that base. It is not anything to do with oxygen because there's no water and no hydroxide in this one-way reaction. And that's what I was trying to articulate before, and I think it's good you asked again. This is the equilibrium. This happens instantly, and then we go back to the equilibrium. Same thing, hydroxide dumped in reacts with the conjugate acid, instantly one-way street, and then we go back to the equilibrium. And I think as we go through this next problem, it might make a little more sense. Okay, so first of all, I'm going to figure out what am I dumping in this solution? Well, I have 2 liters of solution, 2.000 liters. And in that solution, I have 1.50 moles of my A-, my salt, my acetate ion, per liter. So I have 3.00 moles of my A-. And my A- is from the salt, the sodium acetate. We're just using A- as a shortcut, right? Now, also in that beaker, I have 2 liters of solution, and that solution contains 1 molar weak acid, HA, acetic acid, per liter. So I have 2 moles of HA. And that's what is in my beaker, okay? So we have HA and A- in the beaker. Now, I'm dumping in 5 milliliters of 6 molar HCl. 5 mils of 6 molar HCl is essentially free hydrogen ion. So I have 5.00 milliliters that I'm dumping in, and it is 6.0 moles of HCl, which is moles of H plus, per liter. A liter is 1,000 mils. So that is equal to 0.030 moles of loose hydrogen ion added. Now, are you with me so far? That these are the 2 species that started off in my beaker, and this is what I have now, what I'm dumping in. Now, when I dump in that loose hydrogen ion, what is it going to do? It's going to react immediately with the A- and use it up. So that moles of hydrogen ion added is equal to 0.030 moles of A- used up. Okay, does that make sense? This is the tricky part. That's also equal to 0.030 moles of HA that is made. Okay? Not if you get this. Everybody understands that when I dump in the hydrogen ion, it immediately reacts with A- and makes HA. Okay. So now, what's in my beaker? Well, I started off with 3 moles of A- in my beaker. But what did I do? I used up some of that. So I used up 0.030 moles. So what's left in my beaker now is 2.97 moles of A- left. Okay, I used up a little bit. What else is in my beaker? I started off with 2 moles of HA. I made some HA. I made 0.030 moles of HA. So now I have 2.030 moles of HA in my beaker. So now we need to find the pH. Now, this is where I take the shortcut. If you want to use an ice chart, what do you need? What numbers do you need to plug into your ice chart? Or what units do you need? Molar concentration, okay? So, in order to change these moles into molar concentration, I have to say I changed the volume. I added 5 milliliters. So I no longer have 2 liters. I have 2,005 milliliters, right? So I'd have to recalculate my molarities. Does that make sense? Okay, that's a nuisance. So we can cheat our way. Because the ratio of the moles is the same as the ratio of the molarity, we can quick and dirty this and not have to do so much work by using the Henderson-Hasselbalch equation. So the pH is equal to the pKa plus the log of A- over HA. Now I'm going to shortcut this. So pKa is 4.74. Plus the log of A-, now I have 2.97 moles divided by HA, 2.030 moles. So that's equal to 4.74 plus the log of 1.46. Now, look back to the top of your page. When we did the pH of this problem, before I dumped in that acid, we were taking the log of 1.50 here. Is the log of 1.46 and the log of 1.50 going to be hugely different? No, they're not. So the pH is equal to 4.74, the pKa, plus 0.165. So that's equal to a pH of 4.91. Now, what was the pH up at the top of the page? 4.92. So our pH changed by 0.01 pH units. Would you say that this buffer did its job of preventing a large shift in pH? Yes, it did. Now, just for kicks, let's compare this to water, okay? We're going to compare this to water. What if I had dumped that same acid into water? Okay, I have 2 liters of water. What's the pH of 2 liters of water? 7, right? pH is 7. Now, I'm going to take that same 0.030 moles of hydrogen ion, loose hydrogen ion, and I'm going to dump that into 2 liters of water. I have 5 mils of acid, so now I'm going to have 2.005 liters of solution, right? So that's equal to 0.015 molar hydrogen ion, loose hydrogen ion. The pH is minus the log of 0.015. and that is 1.83. So in water, my pH went from 7 to 1.83. That is a significant change in pH, is it not? Yeah, that's quite significant. And my buffer took that same amount of proton, loose hydrogen ion, and it reduced the shift in pH to 0.01 pH units by doing its buffer thing, by letting the hydrogen ion attach to the anion and then finding equilibrium. So the buffer did its job. And that's what a buffer does. It prevents large changes in pH. Okay. So now, let's have you try the basic one. So you're going to do the same thing, but you're dealing with a base. You got the little harder one. So first find the pH of a morphinium chloride buffer. Then think about what happens when I dump in 10 mils of sodium hydroxide. So you're dumping in a strong base. That strong base reacts and uses up your BH+, and then you go from there. Okay? Go ahead and do this with your groups on your whiteboards.